In this video, I'd like to work through this particular problem from the Math Excel assignment this week. Lots of you were asking questions about it, and I agree that it's a bit of a challenging one. So I'll point out a couple items that might help you and see if that's enough to get you through the work that's being asked of you this week. As we've been mentioning in class, I think it's a good idea to identify our objective for each problem as well as the constraints. Doing so will help you be prepared better for calculus class when we do optimization problems there, when we solve optimization problems. Those optimization problems in calculus are pretty similar to this, except we use a slightly different technique to find our solution. In this particular case, we're told that we have a right cylinder that's inside of, or inscribed, if you will, inside of a cone. And our job is to express the volume of the cylinder as a function of x. So as x starts to change here, that's going to adjust the radius of the cylinder, of course. And if that radius gets larger, now we're looking at a cylinder that's wider but shorter, and it still fits inside of the cone. And that position can change pretty drastically throughout this particular problem. So that's the issue that we're facing right now. Let's see if we can build that function. So I would say that our objective is to find the volume of the cylinder, and part of the the method to find the volume of a cylinder is the radius of the cylinder to calculate the area of that circular face times the height of that cylinder. And so that radius is constrained or limited by a couple things. Number one, we have the radius of the cylinder is equal to 3 times x. That's kind of interesting. But secondly, this cylinder has to fit inside of the cone. Now, at first glance, that might be somewhat challenging, but the hint here is meant to make this a little bit more manageable. The notion that we have these similar triangles in the cross-section of the cylinder and cone is going to be quite helpful here. We don't have to worry about the three-dimensional shape of the cone altogether. Instead, we can consider, or focus rather, solely on the cross-sections of these similar triangles. So what I'll start off by showing again here is that this triangle in the top of the cone contains a radius, we'll call it, because that's what's being described here, and a height. I don't want to use the letter h, though. Instead, I might just note that the height of that triangle is going to be the result of whatever capital H, the height of the entire cone, minus h, the height of the cylinder is. So that height is h minus h. So the relationship between r and h minus h is precisely the same as the relationship between capital H, the height of the entire cone, and capital R, the radius of the entire cone. So this hint about the similar triangles is enough to tell us that while R over H, that ratio is equal to lowercase r over H minus H, we also recognize that lowercase r is essentially the same as 3x over H minus H. Why that might be so helpful is because we really need this lowercase h in order to calculate the volume of the cylinder. The volume of the cylinder is dependent upon lowercase h and lowercase r, or 3x in this case. And that volume of the cylinder was actually given to us again over here. So with this additional piece of information, we can actually begin to rewrite our objective function in terms of the constraint functions. So again, our objective was to find the volume of the cylinder on the inside, and the volume is equal to pi times the radius squared times the height of the cylinder. That's essentially the area of the circular face times the height of that cylinder. Well, we know that the radius is 3x. That part was given to us over here in this example. But now let's see if we can find out what h is. So we've made one replacement based on our constraint. Let's see if we can make another. Well, by transitivity, if r over h is equal to r, lowercase r over h minus h, then r over h is also equal to 3x over h minus h. And I think we can do a little bit of math in order to solve for h by itself. And in doing so, we'll be able to replace this component over here within our objective function. So since I have two fractions that are equal to one another, we should recall from last unit that we can cross multiply. And that tells me that r times capital H minus lowercase h is equal to h times 3x. And I can divide both sides by capital R, and we're left with h minus h. Let's use two lines here. H minus h is equal to h times 3x over r. Now, I'm going to add h to both sides and then subtract this group back to the left so that I don't have any negative leading coefficients. And that's going to leave me with capital H minus h times 3x over r equals lowercase h. And this is pretty good for us because we've now established what lowercase h is equal to in terms of x, but also in terms of capital H and r. I don't think we have enough information to know exactly how capital H and r are related in this particular example, but they're going to act instead like parameters. So if we knew the height of the cone and the radius of the cone, then we can go ahead and move forward and compute the volume of the cylinder. So if there's additional information in your problem that I'm missing, then somebody, of course, can send me a message and fill in what's missing. But I think this is the best we can do right now. I'm just going to copy this up and over. And I think this looks pretty good. That's a good volume function based on x, but also the parameters h and r. One thing we can do to take this just a little bit farther and perhaps make it a bit more manageable to work with is that this lowercase h is equal to the difference of two values over here. And it would be kind of nice if we had just a single fraction that this was equal to. And as it turns out, we can make that happen. All we need to do is create a common denominator and subtract these fractions from one another. So I'm going to pretend that this capital H was written as a fraction over 1, and I can multiply both the numerator and the denominator of that fraction by r in order to force the common denominator. And so now we'd be left with hr minus h times 3x all over r is equal to h. And also because this h is a common factor across the numerator, we could see this as capital H times r minus 3x all over r also equals h. And so this is potentially nicer because we're dealing with a single fraction now equal to h rather than a difference of two numbers. And if we bring this form of lowercase h up to our example above, and also, expand or clean up this 3x squared, we might end up seeing a volume function that looks more like this. We have pi times 9x squared times h times r minus 3x, all of that over r. And I'm writing this as one large fraction because this expression here is technically a fraction over 1. That fraction that multiplies by this new fraction, we multiply numerators by numerators and denominators by denominators. So we end up with this expression, and to perhaps clean it up even more, we can reorganize this up front here. And I'm going to do so by collecting all of these parameters, and numerical values, so the 9, pi, and h. I'm going to group those together. 9 pi h. I'm going to move the x squared back, we're multiplying by r minus 3x times x squared, and then write that as a fraction over r. Now, to be perfectly honest, each of these three lines are perfectly equivalent to one another, and not one stands out as a better option than the other, but depending on what MathXL asks for and how they request their final answer, one of these might be better than the others in terms of their perspective. So I encourage you to read the instructions very closely and verify that you understand precisely what they're asking for. But again, I would go with probably any one of these three as a result of this problem. Seems like a lot of work for such a messy answer, but this is precisely what we're going after. As long as we can supply the height and the radius of the cone, we can then find the volume of the cylinder based on any x value that we choose from there. So again, I hope that helps. If you have further questions, please let me know, and I'll do my best to answer in a video response. Thanks again.